Okay, I think we're live. Can you double check the stream? Sounds good.
Yeah, we'll do. Let me check. Hold on. Yep, we're live.
All right. All right. Hello and welcome to today's episode of Corecast. I am your host, Tim.
And I'm Mikey.
And I'm Sahil. Welcome, everybody, to a brand new, exciting episode of Quirkcast. We're back after a 2 week hiatus, but we got some action-packed points for you all to digest. So before we get started, a few logistical things as usual. If you haven't already, do join our Discord channel. And if you're watching on YouTube, where we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, do ask us questions during the episode. Small asterisks, apart from the past 2 weeks. We try to do this every Tuesday. So yeah. So let's get to it. Um, so this is an interesting topic. I think you know, when people talk about science, even beyond just physics, people have the notion that science proves facts. So if we just go towards physics specifically, I guess why can't can I say that gravity exists? Because if I drop an apple and it falls down, you know, clearly there's gravity pulling down on it. So doesn't that prove the existence of gravity? I guess that'd be one question I would pose. So maybe we can lay the groundwork and then answer a question like that as we go through this episode. So I guess Mike, you know what? You look eager. I'm gonna point to you. Start us
Yeah, I
off.
mean, I think yeah, I mean, okay, so this is a kind of a complicated subject, but I think you can make like a very succinct point right away that we can maybe try to unpack later. But I would argue, yes, you're correct. No, I cannot prove that gravity always pulls forces downward. And it's annoying because for some reason everyone, like the whole population of people, have it in their head that science is about proving things with some kind of absolute reliability. Okay, you know science proved this, so therefore we can have ultimate faith um, on what will happen from now on regarding this. And it really just doesn't work like that, and I don't know where it came from, right? The simplest example, I think, is the one you mentioned. Let's say I have a theory that gravity always pulls things downwards. Like it's not even a theory of gravity. It's not even about attracting like objects.
Mhm.
Like, so if I just have a theory that things fall towards this direction that we call down when we drop them, right? You can try the experiment as many times as you want, but you can't give me 100% assurance that if you try this experiment tomorrow, it won't go upwards. Maybe there's some, part of the theory that says, things fall downwards, but 0.000000001% of the time they might fall upwards. Like you can't give me 100% confidence in your theory that things always fall downwards. Just in principle, like you can't. What you can do, and what we are doing in this process, is every single time we drop the ball, we're accumulating evidence for the fact that uh, there seems to be a force called gravity that seems to, at least for us, pull objects towards the ground. We're accumulating evidence for that. Um, and the more times we drop, the more times we see it falls downwards over the fraction of times that it falls upwards. That's it's the accumulation of evidence. And then for most people, we can agree that there's a threshold point above which we say, okay, we accept this to be true. Um, with the caveat that I can't guarantee that this is 100% true. So there is no proof in science. That's not the job of science. Um, in mathematics, you can make proofs, and I don't know how these things got conflated. So that's my rant. Anyways,
Fair enough. Fair enough. I guess maybe it might be nice to do a little bit of historical kind of overview of this type of question. Maybe starting with the scientific method. I think there's a sense in which, like as you described in Mikey, that people have of like, oh, you test the hypothesis, and then you do run some sort of like there's like a whole formulation. You determine, oh, should I like accept or reject the null hypothesis and stuff like that. But maybe it might be helpful just I guess, Tim, could you describe what the scientific method is, philosophically and like practically speaking?
Yeah, I think this is like intros to science 101, right? We always know that physics ultimately is a practical discipline. So we build theories, or hypotheses, and we run experiment. And then we try to reject hypotheses. So physics, like all sciences, has almost like a conservative bias, right? We always I mean, also if you ask ChatGPT, right, you immediately get the answer that we never prove something, and we always just disprove possibilities. So there's this notion of falsifiability. Science is always about rejecting one hypothesis. In order for us to, quote, prove something, or meaning establishing a theory, you, like Mikey said, you just have to accumulate mountains and mountains of evidence, but ultimately you never truly prove anything, because the moment one experiment, it's in conflict with your theory, in some sense your theory completely falls apart. But in any case, this is sort of the very, very naive basic understanding of the scientific method. I think the whole point of today's episode is that with modern physics, that actually doesn't really work anymore, and because of a few reasons. First of all, modern physics is the era of big science. It's not like you can simply drop an apple and run the experiment nowadays. And it's also not so easy to interpret the results. So as a consequence, modern physics has become more and more mathematical. Yeah. And certain results for modern physics also cannot strictly be tested experimentally in the same way. And therefore, the scientific method, it will be foolish for scientists or for modern physicists to apply the strictest sense of scientific method. And if we do that, we're kind of robbing ourselves of scientific progress. In fact, I would argue that a lot of breakthroughs have occurred not strictly from applying the scientific method. And I think that in the modern physics, whether physics can prove something or disprove something, that has to be much more nuanced.
So just out of curiosity, if I could, when you say modern physics, what are you thinking, like last 20 years or like last 100 years? Because I would argue that what you said is true, even if you think of physics over the last 100 years, in terms of like what's a motivator for progress. Like you could even say, like, when Einstein was doing his work, experimental evidence was one of the motivators, but it wasn't his main driver.
Yeah, I think personally, I would quantify modern science as the event, after the quantum physics began. But, I see that some of Einstein's work, of course, also has some of that flavor. But probably like the 20s, 30s, it's the mind. There's a shift of mindset a little bit, I guess.
Yeah.
So are you?
Okay.
Oh, go ahead, Mikey. Sorry.
No. That was going to be yeah.
Okay. So actually, this is interesting. You bring up Einstein's theory. Let's actually delve a little bit more into that. So with Einstein's theory, clearly at that time, I don't think there were you couldn't verify all the predictions made by the theory. I think it's maybe like 100, around order of magnitude 200 years later, they finally show like detection of gravitational waves as an example. So I want to really go into what you were talking about with regards to not being able to perform the experiment, and then theoretically, like, if you can prove a statement mathematically, why is that not the same as, like, I guess, proving it in actuality in some sense?
Well, let me just say that when Einstein first come up with theory of, special theory of relativity, I think there are different mathematical approaches. So Einstein's view is that space and time are relative, but then there are different views. But I don't know the history of science too much. Is it like Lorentz or whatever? There's some more mathematical views that says, hey, maybe space just changes. but it's not relative. Somehow the experiment,
Are you talking about like alternative theories to special relativity that were out at the time?
Yeah, I'm not talking about alternative theories, but sort of the interpretational matters, right? Like Einstein's theory of special relativity has an interpretational aspect. He's saying that, hey, space-time itself is relative, but and from the same equation, you can have a different viewpoint. You can say that, well, maybe it's not that space and time are relative, but the experiment kind of colluded together to give you those results. And you can say that both of these theories kind of give you the same outcome. Like experimentally, they're not really distinguishable in that way, at least at that time period, right? But as time goes on, I think there's something to be said that Einstein's theory is still preferable solely because of the way it views space and time. And later on, many years later, Einstein discovered the theory of general relativity, and that takes the viewpoint that space-time itself is malleable to the extreme. It can curve and whatnot. And then I would say that the other picture is completely just erased, right? It's just like it cannot be generalized anymore. So in some sense, like Einstein's theory triumphed, but I would say it's not 100% because of the experimental evidence. Of course, like if the experimental evidence contradicted Einstein, of course the whole thing will fall apart. But it's more than just the experimental evidence. A large part of it is the beauty, the interpretational aspect of Einstein's theory. It's telling you, hey, look, there's a fundamental new picture, a consistent new picture of what space-time is that makes it so powerful.
Yeah, no, that makes sense. I want to also, I guess, discuss, the example of dark matter, for instance, where we've talked about this in a number of previous episodes, where people are trying to like figure out what it is, and so far none of the experiments have turned up anything. We did a whole episode on how dark matter is getting darker. So you just have this theoretical, I guess, explanation that, oh, it's just this like matter that doesn't really interact with light, but you can't experimentally verify it at the moment. I mean, it seems like more evidence is going towards that. But I guess two questions is like, can you frame it in the context of this discussion? And then what is the point that you reach where you accept like, oh, this dark matter is actually a thing versus like some other alternative explanation?
Can I actually segue into that with something in between without getting into dark matter first?
Please
Can you hold that?
Please do.
Okay,
Please
because
do.
I feel like there's a thread that's kind of in common, like with this whole special relativity thing. Like, and kind of goes off of what Tim was talking about. You could almost imagine like, well, I guess the point of, Tim's discussion, if I were to interpret it, would be like, there are reasons why we have, you could call it faith or confidence in Einstein's theory that go beyond just strict experimental evidence. And I just wanted to take a minute to maybe like elucidate my interpretation of that, which is like, there's one way, as Tim mentioned, to interpret special relativity as like this beautiful structure in space-time, or you can just imagine it as like, a set of equations that just give you results, and you can say, okay, that gives you the same result, basically just repeating what he's saying. But the thing that makes that beautiful structure special is the number of other things that it explains, right? So once you assume that there's this beautiful structure, you get other things for free. Like a lot of people don't know this, but the fact that particles have spin, like we talked about in the previous episodes, the fact that particles have spin that kind of goes like in either 1/2 times a certain number, or it's basically an integer decremented angular momentum. That comes like the structure of special relativity explains that. If you assume that the equations are just all separate things without some bigger structure, then you have to explain each of those things individually. But if you have one idea that explains 1,000 things by accident, like you didn't even expect it to, but you just find out later that it does, that builds some confidence in us. And I think you could literally, I don't think it's that hokey. Like literally, you could just think that you could measure the explanatory power of a certain, it doesn't have to be a theory, but a certain interpretation of a theory. Like how much does it explain? So in some sense, you could say that that's linked to experimental verification, right? Because let's say it explains this experiment or explains this experiment, explains this experiment, but it's not limited to that. Like there are certain ideas that we can interpret from the experiment, and another theory could explain the structure of that interpretation. So it's, as I said, it's a complicated thing, but I think you can really apply this to dark matter too.
Yeah, and I would add that, so dark matter is a good example because it's science in progress. We don't know what the answer is yet. Einstein's theory is sort of something in the past. We know Einstein is mostly right. And I think in colloquial speak, we'll say that Einstein's theory has been proven right. I think that's fair to when we talk to the general layperson. The proof is as good as
that.
yeah. So, but we're not talking about that. We're not talking about that, of course. But this brings up a good point. Like online, you can see a lot of discussion says, "Hey, Einstein is wrong. Oh, maybe Einstein's theory is wrong because, let's say, neutrino moves faster than light, right?" But there's a reason why, even if we find out that neutrinos can move faster than the speed of light, let's say that happens, Einstein's theory is probably still not wrong, because Einstein's theory isn't just about, the having an ultimate speed limit. It has many other things. Even if there were one experimental fact that falsifies some parts of Einstein's theory, we're not going to just throw the whole thing to the trash, right? And that's how science nowadays really is. Like we know that theories. There's no theories that are 100% correct, but and also the old theories, even though they're demonstrably false in some conditions, they're not 100% wrong either. They are still useful in their own regime. So I would say that if we apply that to the story of dark matter, then we see that the theory of dark matter, while it's not 100% correct, you can argue that it's probably pretty good. We're probably not too far from that, but there's still some distance away.
Mikey, I noticed you had a reaction when Tim said neutrinos faster than light.
Oh yeah, I think if he chose that example due to its absurdity, and absurdity is a matter of taste. Maybe I thought it was a little too absurd, but okay, no. But then I did think about it, and the only other way I would say it would be like let's say we found that under some conditions neutrinos can move faster than the speed of light because, well, okay. The only reason I made that expression is because, going back to the whole accumulating evidence thing, we've measured a lot of neutrino velocities by now, and we've accumulated a lot of evidence for the fact that neutrinos don't move faster than the speed of light. So if we did see a neutrino moving faster than the speed of light, I think it would be a first and very reasonable assumption to say that the experiment is wrong. Right, we have a huge amount of evidence for this one thing, and you're telling me that we just saw something completely different. Then once we repeat this experiment a few times and maybe observe it again, make sure it wasn't a fluke, then maybe we need to build a theory about why, under certain conditions, you might find them moving faster than the speed of light. And then up until that point, after that, I completely agree with Tim. That, we would consider that an extension of the theory of relativity. We wouldn't. There's so many things that it does explain and has explained well. You can't just throw the whole thing away.
Well, I use this fact because within the high energy physics community, this actually literally happened. I think the experiment.
But the first thing everyone thought was the experiment must be wrong. And
exactly.
It turned out to be the right answer.
Yeah. So I think the caveat is that even though we say we apply the scientific method, but it would be foolish to apply it just completely blindly. You can't just apply the scientific method blindly.
So, this reminds me of as we're going through this, you get some piece of evidence, and then there are multiple explanations of why that piece of evidence may have arisen. In the case of neutrinos faster than light, it could either be experiment was wrong, or maybe the experiment was right, but then like you need to build a new theory around it. And Occam's razor says when you have multiple explanations, you choose the simplest one, meaning making the fewest assumptions. So can we talk about that, and even segue into dark matter of like how does that apply in physics? And when is that not true? When is it that you don't pick the simplest explanation? And yeah.
It's funny, actually. I think Einstein has a famous quote. What was it? Like, the truth should be, what is it? Like, it should be as simple as possible, but not simpler than it has to
yeah.
be, or something like that.
I think something like that. As simple as possible,
Yeah,
but
I
not
mean,
simpler. Yeah.
yeah. But I think, okay, so I think basically what he's saying, kind of in a funny way, he's highlighting like how kind of careful you have to be when using Occam's razor, right? You can't, obviously Occam's razor, you can't take that super literally too. Because the simplest thing would be to just have nothing existing. So obviously, I don't know, you could agree with this or not, but I would say that pure existence already means that Occam's razor taking literally should not be a rule of thumb. But I think there's one sense in which Tim and I are both speaking about, in which we do apply Occam's razor, where, and maybe this is my interpretation of what Einstein said, but um, like, um, and it goes back to what I said before about one theory being able to explain multiple different phenomenons, things that even seem unrelated. Like when that happens, when you have a theory and you weren't even expecting it to explain this other thing that seems totally unrelated, and you find that it does. Um, just emotionally, you get you have some confidence in that. But I think you could actually like quantitatively measure, like literally, how how complicated is your idea, and literally how many phenomenons does it describe? By that metric, special relativity would be off the charts. Just very simple framework explaining everything from nuclear physics to like astrophysics to blah blah blah. Um, maybe dark matter is not as like powerful, but a lot of people don't know it's actually really powerful. It's not just about like we have to come up with this idea to explain one thing. But if you assume that there's something like dark matter out there, it explains mysteries in galactic rotation curves. It would explain mysteries about the early evolution of the universe. It would explain a whole bunch of things that you wouldn't even expect. And if you look at the competing theories to dark matter, they're the opposite. If you assume those, then everything, like you have to, like it's very inconsistent, or it would require you to come up with a lot of exceptions that explain other things. And so, yeah, so Occam's razor meaning like the simplest theory, but that also explains everything. Not just simplest, but simplest that explains the most.
But I would say it is really a fine art to use Occam razor, and in fact, in for dark matter, and we know that dark matter explains a lot, and of course, we still have not literally have confirmations of dark matter yet, and that has caused a lot of papers to be written that applies Occam's razor in a slightly different way, and sometimes it's even somewhat abandoned, at least in its simplest form, right? When people might contemplate, oh, maybe there are multiple types of dark matter, is certainly not the simplest way of having dark matter. You know, having different types of interactions, having but these are all I think, but I think if you talk to any physicist, I think they are aware of the trade-off. You know, you give up on some level of simplicity, but maybe the hope is that you get something out of it. I guess the crux is always that besides experimental evidence, you need some trade-off. You know, it's like it's quite a bit more nuanced. It's a game you play. It's like you optimize, I don't know, like a mixture of different attributes. It's like a game, really.
I would add to that. Certainly, there are many examples in history where a theory was becoming simpler and simpler and simpler, and then something experiment happens that seems to make it more complicated, and it gets more, and then later on you realize after some big insight that this thing that seemed complicated actually makes the whole picture way more simpler. So sometimes on your path to simplicity, you have to explore regions of complexity. I think that's like an important thing to note about Aga's razor. That
yeah, and following the same logic, right? There have been theories that people thought contradicted experiments, but only to realize later that, hey, maybe they didn't think about that theory faithfully. They didn't do the calculation properly, where the theory actually did the experiment really well, but you just, I don't know, guys just did the wrong calculation or interpret things in a different way. So that also has happened. So in some sense it goes both ways, right? That's why, physicists are kind of in this gray area. It's like we can't really prove anything, but we're never disproving everything either. We're kind of in this gray area to, maybe there's evidence for A and B, and then there's evidence against C and D, but it's always evolving.
Well, I would say, like, to be more specific, in fact, I would say, like, what we're trying to do is we're trying to find the simplest structure. So if I said, like, the measure is how simple the theory is that explains the model, we're trying to find the theory that is ultimately simple, that explains everything. That is the goal, right? And so in that sense, it's like, yeah, we're making progress towards that, and there's a huge framework of theories that you could call interconnected theories, or even the same theories that serve this purpose of just, having a structure that explains the most. And yeah, I guess, yeah, just same thing I was saying, like the path towards that, if you were to only use experimental verification, the scientific method, to build that, it would be a really, really difficult task.
One question that I have is, why do we take this as a given that, like, we should go with the explanation that has that's the simplest but has like the widest range of different explanations? It seems more of like an artistic choice, an aesthetic choice, and I'm wondering, like, can you expand upon that? But
yeah. Really glad you asked that, because I would say in one sense it is definitely like an artistic choice, because, like, okay, if I'm saying that there isn't like a very strict protocol like the scientific method that you should use to determine how to progress the field, then then it does lend itself to a certain level of artistry and instinct, and that's the reason why we have like veneration for people like Einstein. Like, he had some artistic vision that other people who had same access to the same experimental data, like, they didn't have that artistic vision. But also I would say that there's a very strong reason for why we favor theories that are simple but explain a lot. Like, just the amount of technological progress that those theories bring about is much, much greater, because if we have faith in relativity, right, it can make a lot of predictions about things that we've never even tested before. But we think we know what the answer is, and we can progress a lot faster if we think we know what the answer is. And so, like, if we had to verify special relativity every time we wanted to make a new, like, semiconductor, right, how long would it take to design like smaller and smaller semiconductors? Like, a lot of that, the speed of progress in technology comes from the fact that we believe we can have faith in these theories to a certain extent because of how much accumulated evidence there is for them. And if we couldn't do that, I think we would never make any kind of technological progress. But, not to say that technological progress is all that's important, because I don't think that at all. Like, yeah, it helps us build technology faster, but also it's like from a point of like understanding the universe, and understanding the source code or whatever. Like, there's a strong feeling that a theory with these properties, there's something closer to the source code of our universe than a theory that doesn't do that for you.
Yeah. Well, and going back to Sahil's point, when you ask why does physics favor theories that are simpler but explains more? I think the first thing is because the goal of physics is to explain. That's fact number one. It's undeniable. Ultimately we want to use physics. But I think another point, yeah, it explains something. Minimally, it explains more than zero. Okay,
that's a very low bar, but yeah. Minimally, physics has to explain
right. So as a result, you always have that bias to explain more. But then what is that? Then the second point is like, what does it mean when we chasing simplicity? I think that's very subjective in some sense, you know, like
Very
and
artistic. Yeah.
yeah, and that's yeah, and that's why it's an artistry. Like, what is the simplest theory? It becomes, I mean, it becomes the job of physicists to defend, and that's why there are theoretical work on that front, right? Like I remember. Nima Kandi Hamed, my advisor, back in the days, like 2 decades ago, it's like 20 years ago, he published a paper called The Simplest Theory. And I think the content of that paper, for most people, they would say that that's not the simplest theory. His theory has like a bazillion different particles, has a bazillion very complicated interactions. The reason he say that the paper is titled The Simplest Theory because he argued that the theory has the most amount of symmetry. And that's why, even though on the surface it might appear very complicated, it's actually extraordinarily simple. I would say like that's the level of artistry, right? Like a theory that looks maybe very complicated could actually be very, very simple. And this artistry is why physics isn't just purely experimental discipline. It's got theory involved, and the goal of theory is to make that simplicity apparent, I would say.
Interesting. I wonder, so in particle physics, it seems like you're heading towards the hope is you get one theory to explain everything. But for things like material science, you have like a different theory for different materials. Is that like how do you draw the distinction between the two things? They're both physics, yet they seem to have like very different approaches. At least
I would say that they're quite the same, maybe just at different depth layers, because like, even in material science, right, there's a lot of progress to be made, like especially in material science with just trying new things. Like we learn a lot of graphene stuff like that, like just kind of discovered by accident. You could just try things and see what sticks. There's a lot of really good progress to be made there. But people still get really excited, like, one of the recent Nobel Prizes was because of advances in the theory of topological insulators. And that's something people are really excited about, because if you have a theory like that works really well, then you don't have to just try random things. You might have a much better idea of what kind of things you can try and what to expect. But even in material science, I think there's a lot of value in having a simple theory that explains a wide variety of possible materials. Although in material science, there's also still much progress to be made the other way. In particle physics, there's no we're way past trying random things. That will never work in particle physics.
Yeah, I would add that in material science there's a theme. I know that there's like a bazillion different materials. You can always engineer new ones. They all have slightly different properties. But I think the theme of theoretical material science is to come up with general universal truths that applies for multiple types of materials. And Michael, you mentioned about topological insulator. I think that research is specifically to pick out the topological aspects of a material. And we're not going to go into details what topological insulators are, but you have a common theory that applies to multiple types of material and able to explain their behaviors in a unified way. And that's powerful. And this is why physics has to go beyond the scientific method. Like these are not things you're going to see in experiment, right? Like if you only look at experimental evidence, you're going to get like every material will have a different theory, right? But if you look beyond that and apply sort of this principles, I don't know, this artistry of having a simple theory that explains a lot, then you have something like, you come up with concepts like topological insulators.
I want to slightly, I guess pivot the discussion into more of, I guess a little bit more speculative in some sense. So we've talked in a number of episodes about the possibility of the universe being a computer that's computing something. And when I look at like normal computers, they can do mathematical statements like 1 + 1 = 2, an exact statement that's a proof. My question is, why can't the same apply to physics? Like, is it just a question of technology, or is it even in principle, like no matter how much you try, like you'll never truly be able to prove something? even assuming the universe is a computer and whatnot.
Well, computers are actually, there's always a non-zero chance that if you type 1 + 1 in a computer, that it's gonna, right? It's
Yeah,
exponentially suppressed, but
I think it's what 10 to the 10. I think computer errors are something like that.
uh,
At least 10 to the
um,
10, I think. Which is what
yeah.
quantum computers struggle with. They have an error that's much larger.
Hmm. And you might argue that the universe is subject to the same kind of like noise issue. Actually, there's some intriguing evidence pointing forth that black holes might be related to inabilities to correct errors in our universe if our universe is a simulation. So yeah, I think that's just it's a difficult question to answer just because of how little we know about the
Mm,
simulation. It could work in many ways that are closer to our everyday computers than we think. Um,
mm,
but I think my personal opinion right now is it seems like the computers we have, right, they were sort of designed haphazardly. There's a reason why your computer changes the format of information. There's thousands of transformations that occur from like the source code to the executable to blah blah that have nothing to do
mm,
with what the computer is actually trying to do. So the thinking is that if there's some more powerful being that can make a much better simulation, it might have some better foresight of designer thought, and that's kind of what it feels like we're chasing when we do physics.
mm.
Well,
And
let me just follow up on that. Back to Sahil's your question. The problem with the problem is if we try to say, hey, physics is mathematical in mathematics you can prove things, why not in physics, right? Is that
yeah.
physics always need context? Like, let's say we take the stupidest statement: 1 + 1 is 2. Like in math, it's just axiomatic. We define 2 as 1 + 1. You can argue that, and then we
Mm,
can take it to physics. 1 + 1 equals 2. You still need some context, right? One watt plus 1 watt, right? So let's say you try, hey, 1 electron plus an electron equals 2 electrons, right? And in principle, yeah, that might be true most of the time. But hey, I don't know, if you toss 1 electron into the black hole and then toss another 1 electron into the black hole, are there 2 electrons in the black hole? Maybe you don't know. Maybe the black hole is Hawking evaporated and there are no electrons. Maybe 1 + 1 is 0, right? Like, or maybe you take 2 electrons and you smash them together, you get an electron positron pair. You get 3 electron and a positron. So is 1 + 1 equals 2 or 1 + 1 equals 3? I think that's the thing. Like, even obvious mathematical facts, when you put in context, it just becomes not so obvious anymore. And that's sort of the difference between math and physics, I would say. Like, in some sense, physics is more, I don't know, like more relevant in that way, and also more nuanced.
mhm.
Mhm.
I guess what I'm trying to get at is that it seems like at least my understanding is when you do experiments, you have noise and you have some uncertainty around the prediction which you made, and there's some like statistical test that you can run to say, oh, this experiment validates the hypothesis or however the lingo is. And then it's purely based on this noise that I like am unsure whether my theory holds exactly. Like say I have a theory that tries to fit some kind of straight line to experimental data that I'm getting. The data points won't lie exactly on that straight line. But if there weren't any noise or anything like that, you would assume it would fit exactly on the straight line. We've talked about a number of previous episodes that the concept of noise itself is like it doesn't really exist. It just exists based on like how we're observing the system. Like nature is doing what it's doing. So from that aspect, I guess what is the notion of proving something? Is it like can it go beyond ourselves or is it purely based on like our like viewpoint and experience? Because then you introduce like all is it a humanistic notion to prove things is my question. Or is it does it transcend beyond us? Like can nature actually prove something is my question to you.
I mean, certainly the idea of proof, like humans cook it up. We have logical systems, and true and false, and proofs are just statements that are true through brute fact of logic. And I think
But
it's
yeah, but the key point is that like for you to prove something too, you need assumptions. You need axioms and you need assumptions typically
yeah.
to prove anything. And in math, it's the study of like having axioms and assumptions and then proving what the logical consequences of those things are, right? I guess in a sense in physics, if we did have a quote unquote theory of everything, and we somehow were able to say with certainty, here's a mathematical structure that explains every single measurement you could ever make. If we had that, then maybe you could one day prove something in physics, but not until that point. Because at that point, you're not sure whether you're talking about this mathematical structure or that mathematical structure. And, there's some look very much similar in some regimes and then look different in another regime. So
yeah.
I think that's why we don't use the language of prove, because to prove something, you have to know something for sure. And we don't feel like that's ever true when we do physics.
You were going to say something, Tim?
Yeah, basically just follow Mikey's statement, right? Like if to prove something requires an assumption, but then that's the problem with physics. We have our assumptions are at best approximate, and even if you bring in quantum physics, we repeat it in many episodes. Even the most sacred quantities that you can physically or possibly imagine, any quantity that you can measure, are probably approximate. So at the end of the day, you never have your assumptions completely honed down anyway. And therefore, like the basic, but is it? But have we just proved that you can't? Is it like a logical paradox? Like you just prove that you can't prove anything instead of proof, or is that?
Unless you have some notion that you can have an assumption with 100% certainty, yeah, unless you have that. But you could axiomatically state that we never have that, because unless you look at the end of time, right? Because you would have to do every single experiment possible in order to. Yeah, I think that does serve as a proof that you can't prove anything in physics.
So that itself is a proof?
Yeah, I think so.
All right, so physics is able to prove something.
It's a contradiction.
Yeah, so people should just stop using that language. That's it's a damaging language, because it gives one the idea that their certainty exists, and it's probably used a lot for snake oil salesmen, who I think are well known for the whole strategy is to oversell the confidence you should have in them.
Yeah, and let me just add that like beyond that, it's there's a fundamental problem. We are also part of the system. I mean that's one of the fundamental limits. Beyond everything we've discussed, right? We can never have a bird's eye view of the universe. Like we are part of whatever the universe is computing right now, and it's never possible to completely extract ourselves from that. And as a result, it's like you can't. There are just limits on what we can do.
If you define a threshold, then you can prove things, quote unquote prove things. If you say like, okay, after this amount of evidence, I'm going to say that this theoretical thing is an assumption, then okay, you can technically prove things, but your results might not agree with what people find out later if you restrict yourself to that. Threshold. It's important to think about this thing without thresholds, I think, to make progress. It's important not to think that you're proving things.
You saying that
it's hubris to think so?
Are you saying that if you had an infinite amount of evidence that supported, your hypothesis, then there would be a proof that this is true?
Yeah, but I think I would say yes, but I think the point I'm trying to make is that that's impossible. Just even conceptually, it would be impossible to have like 100% evidence, because unless you've seen all regions of space and time, unless you've explored all regions of space and time, can't say that. So
this kind of reminds me of a statement my friend made. I think he quoted from somebody else that it takes an infinite amount of data. It takes like an infinite amount of data points to falsify any probabilistic theory. So is that kind of similar in some sense, or
is that true? Because most probabilistic theories will tell you what the shape of the uncertainty could be. So we do certainly rule out probabilistic theories with fewer than an infinite number of measurements.
Yeah.
Well, you
but
statistically rule them out, but they could be true. Just could be, just collect more data and
yeah,
maybe
it could be that you
eventually.
just there's a cosmic conspiracy possibility that like maybe the universe just happened to make it like the one it's like the Boltzmann brain thing, right? Like it's possible that yeah, so in that sense, yeah, maybe it's true that it's impossible to disprove.
Yeah, and also technically, the universe violates all the axioms of probabilistic theories, right? Like for example, things are, data points are independent, and quantum physics just tells you it's not true. There could be correlation, from between here and Andromeda. So
there could even be correlations between here and parts outside of the universe.
yeah, so so technically the independent data point assumption is completely flawed, but science still goes on.
Yeah.
I wouldn't say that. Well, is that an assumption of science? I thought that isn't necessarily that's an assumption you may make during the experiment, but isn't necessarily an assumption made by probability theory. Maybe what you could say is like the probability of finding a particle in any one given location doesn't necessarily sum up to one, because there could be an event that happens where it just disappears. Some other particles appear, so it no longer exists anymore. Is that a fair statement?
Yeah, I mean, yeah, if it's connected to some other part of the universe, it would certainly look like that. I mean, some part outside of, our patch of the multiverse. That's certainly what it would look like. But we've never observed that. So unfortunately, if we ever observed that, it would be evidence for, connections outside of our observable universe.
Yeah. And I want to ask two audience questions that I've been sitting on for this whole episode. So the first one, this asked a while back when we were talking about dark matter. This is to be fair, have we observed dark matter in the form of neutrinos and black holes? Question mark.
No, we've concluded quite simply, like according to all accounts, the amount of neutrinos and the amount of black holes would not be enough to account for dark matter. So I think at least these days, we, of course, maybe there's some issue with the way we've been measuring neutrinos and black holes. Maybe we've been missing like a whole bunch of them, and maybe they could account for it. People have done countless experiments to try to see if this is the case, and all point with the same answer, which is no. But again, we can't rule that out. But was that question really related specifically to neutrinos or black holes? Because
Yeah,
it said both. The question was asking about both.
Yeah. Well, just as a basic physics lore that people might not know. So if dark matter is something like neutrinos, it basically would be what we call warm dark matter. It's going to move too fast, and it would destroy some of the structures of the universe. And for that reason, and many other reasons, neutrinos are not dark matter, and dark matter should be unlike any types of neutrino we've seen so far. And as for the issue of black holes, if black holes make up a good chunk of dark matter, you can imagine what black holes do, right? Given the amount of mass they have, they could really very much disrupt the way galaxies are. They can consume materials and whatnot. And so if dark matter was black hole, these have to be really weird black holes, not the common ones you see. And we have not observed them, so yeah. Black holes and
although it's worth noting that people have come up with plenty of theories of weird black holes in an attempt to fit them into dark matter, and some of them, work better or worse than others. So it's not something that's completely ruled out. Or the thinking is, if dark matter, some parts of dark matter are made up of black holes, maybe dark matter is made up of a bunch of different stuff, and maybe like 5% of it is black holes.
Yeah. And I guess to evaluate things like this, you can apply what we described so far. Like, is the model simple in certain ways, and does it explain more than the theory is created to explain? If it's just there to explain dark matter, it might not be the best theory, right? It's just one thing. So that's why people generally don't like theories that dark matters are like neutrino at least the light neutrino or like black holes. These are not favored theories. They're not impossible, but not the best theories right now, I think.
Gotcha. And then the second question is, what limits are imposed on theoretical physics by Gödel's incompleteness theorem? Maybe we can briefly describe what the incompleteness theorem is at a high level and then answer this question.
Yeah, I mean, for my limited understanding, it's not a mathematician. But anyway, if I look at some of the proof, what Gödel's incompleteness theorems entail, it tells you that if you can enumerate theorems, like proofs, like 1, 2, 3, 4, 5, 6, 7, 8, they could be infinite. Then there must be some statements that are contradictory, meaning that it's incomplete. Like there are theories that cannot be proved or disproved. And people have shown this, have shown that there's certain statements, there's certain systems in quantum physics, and that you cannot prove or disprove either way. Like if you have a quantum system. And I suspect that might be true. The world is quantum mechanical. There could be statements like, I can't even imagine what the statement would be, like something to do with particles, whatever, X, Y, and Z, that can neither be proven or disproven, but maybe it doesn't matter that much, right? Because the universe will still run, regardless whether something is proof or not.
Wait, isn't what we're saying even more drastic? Like Gödel's saying that there will be things you can't prove. We're saying
you can't prove,
you can prove.
That you cannot prove or disprove. Yeah.
Yeah.
I mean, so certainly some statements in theoretical physics is definitely incomplete. Like it can neither be proof or disprove. So that has been shown to true, especially for quantum mechanical system. And I have no doubt, and probably things related to cosmology. Things like, is there a multiverse out there? I don't think it has to do with Gödel's incompleteness theorem, but this is sort of in that realm, right? Like, do we know for sure? Do we never know for sure? So I don't know. But in my mind, it's probably that Gödel's incompleteness theorem will apply for physics. But on some level, maybe it doesn't matter that much. Like it doesn't matter too much whether humans can prove it one way or another. Maybe it's like, okay.
Yeah, it seems like a much more like almost in a sense like a too refined of a discussion. Like we're talking about how like it's almost impossible to say you could prove anything. What we're looking for is, even because it's of that impossibility, what we look for as physicists are even things that could be considered like artistic hints or what ideas to follow, just so we can make progress. Gödel's over here talking about like, for exact systems, you can prove or disprove certain things. You can prove or disprove other things. Like we're not even close to having the luxury of being able to like make those distinctions. We're just the job of a physicist is to make progress in this knowledge framework, I would say. So it seems very distant to me.
Mm-hmm. My knowledge of this is that there are some problems in material science that are what's called undecidable. I don't know the exact details, but what I know is that these are approximate models, and so it just comes from sort of the approximations that you use. Anyway, so we're almost at time, and so I wanted to give you guys a chance in our tradition to leave the audience any words of wisdom that physics and whatever synonym for proof that you want to use have taught you to appease Mikey.
Yeah, okay, so I guess I'll go first. And I just think that there's I think that there's philosophically a serious problem, not just philosophically, but like I think it's bad for like human education and knowledge to like associate the word proof with science, because it's almost like the opposite of what you want to do. Like, proof means you have 100% certainty, you can stop questioning certain things, but we're at a point in science now where that is not a good strategy for making progress. And if we insist on, it's like, I think it's a rather primitive notion that science experiments can prove one thing or create certainty in some sense. Like, of course, there's a long history where we sort of approximate that, where we say, okay, there's so much evidence for this. Maybe it's okay if people just call it proof, because we're so confident in this. But now people are starting to like use that word, I think, against what was intended for it. And I think it's time to just stop using it and just be aware of the uncertainty instead of getting complacent with some notion of certainty.
Yeah, I guess I would somewhat agree with that sentiment. And also, I would say that the word prove and disprove a lot of times is quite lazy. It's like, hey, we have this thing, and all of a sudden, it becomes black and white. And of course, I hope we're not saying that all of a sudden science is wrong. And that's far from it. It's and precisely because you can never truly prove or disprove 100% anything. And that's why science is powerful, because it always has that, however small or large, it always has that possibility to change, basically. And I think that's something we should focus on. And also, I don't want to dissuade people on thinking that, hey, science is such a black and white subject. It's either something's right or wrong. A lot of times, actually, it comes down to a level of artistry, like a sense of what's I don't even know. It's somewhat subjective, right? What's beautiful, what is palatable, and if we are honest to ourselves, I think that's probably the bigger component of what drive modern theoretical physics. Of course, that's not to underscore that experimental evidence is extremely important. All this game, you can think of the experimental evidence kind of like the canvas at which scientists will paint something, right? Of course, you need to have a canvas first to paint something, but other than that, you need a sense of knowing what's good to paint, and that's what distinguishes a good physicist from just an average one, right? Yeah. So, and
What's
I think
amazing, though, I think just to real quickly, is that there is this distinction where people that paint seemingly very beautiful things, it actually creates new canvases, and that's something you don't see in art, but that's something that definitely happens in physics. So, yeah.
Yeah, well said, well said. And so on that note, I want to thank you for joining us. We'll see you